Okay, so let's just give a brief recap of the things that we discussed last time. We were discussing heterotic compactifications from 10 down to 4 dimensions, and we wanted to preserve n equals 1 supersymmetry in 4 dimensions. So we took a Kaluza-Klein ansatz, 10-dimensional space, Slinkowski space times x6, and we looked at the 10-dimensional supersymmetry variations, and we tried to find a non-trivial solution. That is, we wanted to find an unbroken supersymmetry transformation which preserves 4-dimensional Poincare invariance. And we also set the fluxes, the flux of the B field to 0. And once we did that, we were just left over with these two equations. We had a spinner, epsilon 6 plus, a positive chirality spinner on the internal manifold x6. And we found that the spinner has to be covariantly constant. And so this is a condition both on, a condition on the metric on x6. And we also found that this contraction of the field strength of the gauge field, Fmn contracting with gamma mn acting on epsilon 6 plus has to vanish. Okay. Then we went into a long discussion about the meaning of these constraints, the geometric conditions that they impose. So the condition that you have a covariantly constant spinner means that you have reduced Escher-Through holonomy, or equivalently, that x6 is a Calabiyau manifold. It means it's a complex manifold. It has a Kähler form which is closed, therefore it's a Kähler manifold, and it has a vanishing first Chern class. And there was a theorem of Yau which tells us that for any such Calabiyau manifold, there exists a unique Ricci-flat metric which is with a given Kähler class and a given complex structure. In particular, we were interested in the deformations of these structures. So the deformation of the metric then is, by this existence and uniqueness, is just given by deformations of the complex structure and deformations of the Kähler structure. And so these are deformations of the metric. And then we discussed Hodge numbers, HPQ, which were homology groups, complex analogs of the Rahm homology groups. And we saw, well, very briefly at least, that the dimension of this complex structure moduli space is counted by h21, and the dimension of the Kähler moduli space is counted by h11 of x. And these were in fact the only independent degrees of freedom in the Hodge diamond. Everything else was either 0 or 1 or related by symmetry. Okay. Furthermore, we had a B field. The B field deformations, basically, you have another h11 deformations of those, and they end up complexifying the Kähler moduli space. Yeah? Okay, then we moved on to this set of equation involving the field strength, and we saw that this is this can be rewritten as the Hermitian-Yang-Mills equations, saying that the 0,2 part of the curvature has to vanish, and the Kähler trace of the curvature has to vanish. And then we discussed that again, much like for the situation for Calabiyau manifolds, where we don't know how to write down explicitly a Ricci-flat metric. So here too, we don't really know how to write down explicit solutions of these equations. We could reformulate this problem as saying that a Hermitian-Mills solution corresponds to a holomorphic polystable bundle. Okay? So Hermitian-Mills implies holomorphic polystable is the easy part. And then again, there was a difficult existence proof that tells you that holomorphic polystable applies that there exists a unique solution to Hermitian-Mills. Okay. So that's good so far, but now we sort of want to have an analog of the story we have over here. So we have now an existence and uniqueness, so we got up to here roughly, existence and uniqueness of the Calabiyau metric. And in here we discuss deformations of these structures, and or Kaluza-Klein reduction if you wish, the effective fields that you're left over with in the 4-dimensional effective theory. And so now we want the analog of that for the gauge sector. So we want to understand the deformations of these bundles. They correspond to the massless fields in the 4-dimensional effective theory. And again, we have a similar problem as we had in this case. So we can't write down we couldn't write down the Ricci-flat metric. We can't write down the Hermitian-Mills solutions. So if we want to learn anything about the Kaluza-Klein reduction of the gauge sector, we had better invent something that doesn't depend on the explicit solution to these equations, because we can't write down the solution to these equations. And indeed, so that leads us to Dolbeault homology. Okay, So remember that since the 0 to 2 part of the curvature vanishes, right? The 0, 1 part of the connection squares to 0. And so on holomorphic bundles, you can define an analog of the Dolbeault complex, which take values in a holomorphic bundle. So we previously discussed Dolbeault homology just for p-cube forms. And now we're going to discuss Dolbeault homology for 0, p forms, which are valued in a holomorphic bundle. So in a holomorphic bundle, you have this operator, the 0, 1 part of the connection, because f02 is 0, this squares to 0, so this is a complex. And we can look at the homology, and we can look at the kernel of this Dolbeault operator, and we can model out by the image of this Dolbeault operator. And by the way, incidentally, so I've written a sub A here, and I forgot to put it over here, but it doesn't really matter. As we saw, if you're in the situation where you have a holomorphic bundle, by a complexified Gates transformation, you can actually set the 0, 1 part of the covariant derivative to 0. Okay, so this is a set of homology groups, bundle-valued 0p forms with some equivalence relations and some holomorphy relations. And so the degree here in general goes from, so in the Calabiyau threefold, it could be 0, 1, 2, or 3. Okay, and these homology groups have various interpretations, and in fact they're exactly what you need to discuss the Kaluza-Klein reduction of the gate sector and derive the low-energy effective four-dimensional theory. Okay. So the claim is as follows. Let's first look at the p equals 0 component of these degree p equals 0 Dolbeault homology group. So V here is an EA times EA bundle or an SO32 bundle for the heterotic string. Okay. And claim is that the degree 0 homology counts the unbroken Gates generators that survive in the four-dimensional effective theory. Okay. So we had this huge 10-dimensional gate symmetry, which was either EA times E8 or SO32. And by compactifying it, you're spontaneously breaking most of that gate symmetry. But there's a few Gates transformations that are unbroken that survive in the four-dimensional theory. And it's this Gates group, it's this homology group that counts these generators. Okay. In fact, there's a nice Lie algebra structure on these things, and that corresponds to actually the Lie algebra structure on the of the four-dimensional effective four-dimensional Gates theory. Okay. The other one we'll be interested in is the degree 1 homology group. So it turns out that the degree 1 Dolbeault homology describes the deformations of the holomorphic structure on the bundle, and the deformation of the holomorphic structure, well, deformations of the structure which preserve preserve some kind of Hermitian-Mills condition. And so deformations in general give you massless bosonic fields in the effective four-dimensional theory. And so therefore this counts massless bosonic fields in the four-dimensional theory that you get from reduction from the gate sector. And of course with supersymmetry they will be paired up with chiral fermions into chiral superfields. Okay. You may wonder, so I'm not really going to discuss it, you may wonder about the other degrees. So there's also a degree 2 homology, for example, okay, that also has a significance. It doesn't really count matter or something like that in the four-dimensional theory. It turns out to count certain obstructions to these deformations. In other words, it describes interactions, it describes superpotential terms. Okay, so understanding why this is true is not really all that hard. I've written it up in the notes, but perhaps I don't want to spend too much time on it, so I'm just going to take this as given. It's really not all that hard to understand. I mean, these are the global holomorphic sections of the bundle, basically. So the claim is that the global holomorphic sections of this E8 times E8 or SO32 bundle are the unbroken gate symmetries. Okay. I'm just going to use this and illustrate this with an example. But if you're at all interested in this, it's not hard to understand why these claims are true, and you might want to check it in the notes. Okay. Okay, so I want to apply this to probably one of the most famous examples of string compactification, semi-realistic string compactification, which is called the standard embedding. What do we do? So we're going to consider the E8 times E8 heterotic string. Okay. And these two E8 factors, at least to leading order, they don't talk to each other, so I can just focus on one E8, and I can do something similar for the second E8, but ignore it because it doesn't talk to the first E8. Okay, and so now what we're going to do, we need a solution. Remember that we need some kind of solution to the Hermitian-Mills equations. And last time I gave you a canonical example of a solution to the Hermitian-Mills equations. Namely, you can just take the spin connection, the standard connection on the holomorphic tangent bundle of a Calabiyau threefold. Okay, that's a SU3 connection. So that's a nice Hermitian-Mills connection, so why don't we try and use that one? Okay, this is called the standard embedding. Means that you take your E8 connection to be the spin connection, the SU3 connection that you get from the holomorphic tangent bundle of your Calabiyau threefold. Okay, so now to understand the low energy effective theory, I then want to, so we take this SU3 connection. So we started with a connection which sits in the adjoint of E8. Okay. So the adjoint of E8 is a 248-dimensional representation. And now I want to decompose it under the maximal subgroup SU3 times E6. So E8 has a maximal subgroup SU3 times E6. And so the spin connection obviously is going to be identified with that part. And so now let's just decompose this 248-dimensional adjoint representation. And it decomposes into 4 pieces. So the first piece is the 327, where the 3 is the fundamental representation of SU3, and the 27 is the 27-dimensional representation of E6. Then you get the complex conjugates. Then I get the 178, so it's the singlet of SU3, and the 78 is the adjoint representation of E6. And finally I get 81. The 8 here is the adjoint representation of SU3. Okay? So now I want to take my Dolbeault homology, and remember these Dolbeault homology groups are really 0p forms valued in a bundle, which is the adjoint representation of E8. Okay, so now I take this adjoint representation and I decompose it into these pieces and identify the various representations of SU3 here with various bundles that they correspond to. Okay, so then we get a decomposition of the Dolbeault homology. And okay, so you get, there are 4 pieces here, so I'm going to get 4 pieces here. So let me just discuss the first one. So the 3 here, so you want to remember that tangent vectors transform under the SU3, transform as the fundamental representation under the SU3 holonomy group. So you do parallel transport of tangent vectors, right? The tangent vectors form a representation of SU3, and that's exactly the fundamental 3 dimensional representation of SU3. Okay, so this piece here from the 3 here, you get the tangent bundle. Okay, and SU3 doesn't act at all on this 27. Well, you get some multiplicity, which is a 27-dimensional representation of E6, and so that's that multiplicity that you have over here. Similarly for the 3 bars, the anti-fundamental representation, well, it's cotangent vectors which transform in under holonomies as the anti-fundamental representation of SU3. So from that piece, I get this one. And then from this one over here, this is a singlet representation of SU3. So here I just get a trivial line bundle. O sub x here just denotes a trivial line bundle. So as a space, it's just x times a copy of C. Complex plane. And this one here, this turns out to be some traceless endomorphism bundle, right? It comes from 3 tensor 3 bar and project out the trace. Okay, so now given what we said on the previous transparency, just if we flash it again, so now we want to look at the degree 0 and the degree 1 cohomology. For p equals 0, what do we get? Well, let's look at the first piece here. So we get something that transforms in a 27-dimensional representation of E6. How many of those do we get? Well, H0 of Tx, which is global holomorphic sections of the tangent bundle. Okay? But the tangent bundle of a Calabiyau threefold doesn't have any global holomorphic sections. Basically, that's a stability condition. if it had a global holomorphic section, that's essentially a map from a trivial line bundle into T of x. In other words, it's a holomorphic, defines a holomorphic subbundle of T of x. But the degree of a trivial line bundle is 0, and the degree of a SU3 bundle is also 0. Okay, so you would have, so this would violate the stability condition, but we know this is stable, right? We discussed quite some extent that this satisfies Hermitian-Mills, so that's a stable bundle. So this degree 0 cohomology group is 0. You don't get anything from that. Okay. Similarly, I've told you that for adjoint, the other associated bundles which you construct from this are also stable. So the cotangent bundle is also stable, and H0 of that also vanishes. This anamorphism bundle, H0 of that also vanishes. And so the only piece you're going to get is this piece. And this is HP of O. That corresponds to the Hodge number H00 of X. And given the relation between the Hodge numbers and the Betti numbers that we discussed, this is just B0. In other words, it's just one-dimensional. Okay? So you're just going to get a single copy of the 78, and 78 is the adjoint representation of E6. Okay? So the only unbroken gauge generators we get sit in the adjoint representation of 78, and that gives you a gauge field in the 78 adjoint of E6. So we get an unbroken gauge group, which is E6 in 4 dimensions. The next one we want to discuss the matter fields. The matter fields correspond to P equals 1. Okay? So now let's do P equals 1. Well, I'm going to get H1 T of x, whatever that number is, this is the Bow cohomology group, the dimension of this is the Bow cohomology group, times the 27th. So that gives me H1 T of x chirals in the 27. And from this one, I'm going to get H1 T star of x chirals in the 27 bar. And this is going to be H10, it's a Hodge number H10 of x times the 78, but on the Calabiyau, we saw that H10 is equal to 0, so that doesn't give you anything. And from here, you're going to get some H1. Okay, you're going to get a bunch of singlets, so these are singlets of the E6. Okay. Now, what are these things? Again, we can relate this to the Hodge numbers. So what's H1 and T star of x? Well, it's a 0-1 form with values in 1-0 forms. In other words, it's a 1-1 form. So this is just H11 of x. So I get H11 of x chirals in the 27 bar. And H1T of x, what's that? Well, it's H1 with values in the tangent bundle of x, values in tangent vectors. But I can take a holomorphic 3-0 form and contract it with a tangent vector to get a 2-0 form. So these are actually, you can identify this with 0-1 forms with values in 2-0 forms. In other words, these are 2,1 forms. So this is counted by H2,1 of x. Okay, so I get H2,1 of x chirals in the 27. And in addition, I have a bunch of singlets, but they're not charged under the E6. And so what we end up with in 4 dimensions from this, we get E6 gauge group, basically an E6 grand unified theory. If you remember your grand unified theory, this is one of the possible grand unified gauge groups, right? So you have SU3 times SU2 times U1, embeds in SU5, embeds in SO10, and embeds in E6. And with matter in the 27 and the 27 bar, and if you remember your grand unified theory, so all the quarks and leptons sit in a 5 and a 10 bar, which goes into the 16 of SO10, which then goes into the 27 of E6. So this is a grand unified theory with an E6 gauge group. And the net number of generations is given by the difference between these two numbers. So there's H21 minus H11 of x, number of chiral generations in the 27. And if you remember the relation between the Hodge numbers and the Betti numbers, this is actually minus the Euler character of the Calabiyau up to a factor of 2.
So the factor of 2 that comes in the number of generations, that is, I mean, that depends on the embedding that you choose. I mean, if you have chosen a...
The fact that you just have to look at, so what's the Hodge diamond, right? So basically H21 appears twice in a way, right? Because you have H21 and H12. H11 also appears twice really because I have H11 and I have H22. Right, so essentially that's where I get factor of 2. Yeah, so in fact, the Euler character rho is going to be even because of just symmetry of the Hodge diamond. Okay, so remarkably, we started with all this abstract stuff. We started with E8 times E8 heterotic string theory in 10 dimensions, lots of symmetry. Okay, and then we just required n equals 1 supersymmetry. Get a Calabiyau. We get a Hermitian-Mills connection from the tangent of the Calabiyau. We use it to break the gauge group, and voila, out comes E6 grand unified theory with chi of x generations. Now, if you use the quintic, remember the quintic at h21 is 101, and h11 equals 1. So that gives 100 generations. Well, that's very embarrassing. All right. But then there's the Qian-Yao manifold, which I also briefly mentioned. And the Qian-Yao manifold has Euler character 18. And the Qian-Yao manifold had a freely acting C3 symmetry, which you can mod out by, and that reduces the Euler character to 6. And divide that by 2, that's 3 generations. So if I compactify on the Qian-Yao manifold and do this construction, I end up with a grand unified theory of E6 gauge group and 3 generations. That's in fact the reason why the Qian-Yao manifold is very so famous. It was really, well, if not the first, certainly one of the first examples where you just get naturally 3 generations out of a string construction. Okay, so when this story was discovered in the mid-80s, okay, so it's of course quite remarkable. So in quick succession, we suddenly have a complete theory of quantum gravity, string theory, and then you find the heterotic string, which has these E8 gauge groups. It smells like grand unified theory, and then you start doing compactification. And even a fairly simple compactification, like this standard embedding, already gives you a grand unified theory with a very semi-realistic looking thing with 3 generations if you use the Qian-Yao manifold. Okay, so this is all rather remarkable. And so it created waves around the world and spawned lots of magazine articles. In fact, the first time I heard about it was when I was a lot younger. And I learned it from this magazine, this Kijk magazine. It's a scientific magazine in the Netherlands. So just for nostalgic reasons, I thought I'd show you the article. This is from August 1987. Of course, it's in Dutch, so I'm sorry, I'm going to have to translate a few things for you. Okay, it says it's called The Lost World of Calabiyau, and it basically tries to tell the story about Calabiyau compactifications and, of the heterotic string with E8 times E8 gauge group. Okay, so it goes on here, some more pictures, tries to explain how it fits into this, into grand unified theories and the theory of everything, unifying with gravity, and so on and so forth. Okay, so maybe I just translate just for fun of it. I'll translate a few sentences. Okay, blah, blah, blah. Okay, of course, the first sentence in any popular scientific magazine involves Einstein, because Einstein anticipated everything. And, Green and Schwarz, right. According to both scientists, that is Green and Schwarz, there exists an invisible shadow world in 6 dimensions. Mathematicians and physicists have gotten very excited about this new theory. All right. And so on and so forth. Unfortunately, like with most of these articles, there are usually also a couple of errors and some misrepresentations. And the misrepresentations start with this picture. So this is supposed to be an artist's impression of a Calabiyau compactification. So, if I get it right, well, it's explained over here. So I think this over here, the orange line, this is supposed to be Minkowski space, so that's supposed to be where we live. Okay, and you can see various buildings and mosques and other things like that. And then this thing that you see going over here, this is supposed to be the 6 dimensions of the Calabiyau. Okay. And the way the artist has drawn it, it looks like there are buildings and perhaps people living in there in the extra dimensions, in the shadow world. And of course, that's not really the way it works. Okay, but you have to understand the challenges of explaining this to the general public. Okay, so I just thought I'd show it for fun. Okay, so I think that's quite extensive discussion we've had of the heterotic string. So now I want to go and talk about perturbative to-be compactifications a little bit. And this section is going to be quite a bit shorter. There's a lot of things I won't discuss, but there's some basics that I would like to briefly go through, especially because I want to use them as a setup for app theory. Okay, so again, we start in 10 space-time dimensions, and but this time, instead of n equals 1 supersymmetry, we have n equals 2 supersymmetry, which means we have 2 supersymmetry transformations, 2 Majorana-Weil spinners, epsilon 1 and epsilon 2, written here down here, which parameterize the 2 10-dimensional supersymmetry transformations. And the bosonic fields are now a metric. Again, there's an antisymmetric tensor field, and there's a dilaton. This time we don't have a gauge field. This time we have a set of Ramon antisymmetric tensor fields, and in type 2b it's C0, it's a 2-index tensor field, and it's a 4-index tensor field. And this 4-index tensor field has a self-duality condition, which is why I denoted it with a plus up there. Okay? So we're going to do much the same thing. We're going to try and compactify this down to 4 dimensions. Taking the Kaluza-Klein ansatz of the four Minkowski space times x6, where x6 is an internal manifold. And we're going to set the fluxes to 0, just as we did for the heterotic string. The fluxes here being not just the flux of B, but also the fluxes of the Ramon fields. Okay. And then we're going to look for compactifications which preserve some supersymmetries. We want to find some unbroken supersymmetry generators. And okay, so again, then these the 10-dimensional supersymmetry transformations simplify if we set all the fluxes to 0. And okay, so we now have 2 gravitinos, and the supersymmetry transformations are: the first gravitino goes like covariant derivative of epsilon 1, and the second gravitino goes like the covariant derivative of epsilon 2. Okay. So these are exactly the same equations that we encountered in the heterotic string. Okay, so you can solve either one of them, it's equivalent. So you do exactly the same thing as we did before, and you find that x6 has to have a covariantly constant spinner, therefore it must be Calabiyau. Okay. But now comes the difference with the heterotic string. In the heterotic string we only had epsilon 1, we didn't have an epsilon 2. So now when we do this reduction, we're going to get twice as much supersymmetry as we had for the heterotic string. So if we move one covariantly constant spinner, which is the minimal you can have on a 6-dimensional manifold, corresponding to Calabiyau manifold, we now end up with n equals 2 supersymmetry in 4 dimensions instead of n equals 1 supersymmetry. Okay, so we want to break it to n equals 1 supersymmetry eventually, but just for the moment, let's just stick to n equals 2 supersymmetry for a little bit. Okay, so the multiplets for n equals 2 supersymmetry are a little bit bigger than for n equals 1 supersymmetry. So the main multiplets that you want to think about are the gravity multiplet, the vector multiplet, and the hypermultiplet. The gravity multiplet, so the bosonic fields in these multiplets, for the gravity multiplet, it's a graviton and a graviphoton. For the vector multiplet, it's a vector and a complex scalar. And for a hypermultiplet, it's 2 complex scalar, or equivalently 4 real scalars. Okay. Now, again, so you want to compactify, you want to get the massless effective 4-dimensional theory, you want to find the massless fields of 4 dimensions. Now, the reduction of the metric and of the B field is exactly the same as it was before. Nothing changes there. So you can get Kähler moduli, complex structure moduli, complexified Kähler moduli. Okay. But now you're going to have to pair them with modes of Ramon fields to put them together into n equals 2 multiplets. So in n equals 2 multiplet, half of them will be these modes that we discussed before from the NS sector. And now we're going to get another half, which comes from reduction of the Ramon sector, completing n equals 2 multiplets. Okay, so right, so now much like for the B field, if you're interested in the massless modes of these antisymmetric tensor fields, then you're interested in harmonic forms on this internal manifold. Basic reason being, right, that the kinetic operator that you get from the Lagrangian the internal part of the kinetic operator is just the Laplacian, and at least if you impose appropriate gauge conditions, just the Laplacian. And the eigenmodes of the Laplacian, you're interested in the eigenmodes of the Laplacian, and the eigenmodes with zero eigenvalue, the harmonic forms, to give you the massless fields. Of course, there are also eigenmodes with non-zero eigenvalue, and they correspond to the massive modes of 4 dimensions. In other words, they correspond to Kaluza-Klein modes. We're just going to do the massless modes, so we want the harmonic forms. Okay, so for example, let's do vector multiplet. So how do you get a vector? Well, you take this 4-index antisymmetric tensor field, and to get a vector in 4 dimensions, I have one index in 4 dimensions. It means that the remaining 3 indices must be along the internal space, along the Calabiyau. So I want to have harmonic 3 forms on the Calabiyau. And as we discussed, there's for every homology class, there's a unique harmonic representative. So the number of these harmonic classes is counted by the Betti number P3 of the Calabiyau. Okay, and now if you remember the Hodge diamond, how many of those are there? Well, I get H30, H2, which is 1, and then H21 plus H12, and H03. So I get 2 H21 plus 2, so it's 3 forms. And therefore, 2 H21 plus 2 U1 gauge fields in 4 dimensions. Massless U1 gauge fields in 4 dimensions. Of course, there are also massive fields from massive KK modes, which we just do the massless ones. But that's not quite right, because there's a self-duality condition. Self-duality condition effectively relates this expansion, coefficient of this expansion in a given form with its Hodge dual. So the self-duality condition actually eliminates half of them, so we just have H21 plus 1. And now remember that we had H2, 1 complex structure moduli, so H2, 1 of these U1 gauge fields naturally pair up with H2, 1 complex structure moduli into n equals 2 vector multiplet. So that's what we have over here. And then we have one remaining U1 gauge field, which comes from linear combination of H30 and 03. And well, it's universal, of course, because it's for any Calabiyau manifold you have 3 form. So that, since it's universal, of course, it's got to pair up with the graviton in the gravity multiplet. So that's the one you have over here. Okay, similarly, you can find the remaining massless mode. So let's just quickly go through it. So we have these other tensor fields, B2 and C2, and I can expand them in harmonic 2 forms, which give me a bunch of pseudoscalars in 4 dimensions. I can also take C4 and expand it in harmonic 4 forms and get another bunch of pseudoscalars in 4 dimensions. And now remember that Kähler deformations also had to do with 2 forms, right, 1-1 forms. So I can naturally take these things. In fact, remember that these were in fact naturally, so this was in fact naturally paired with Kähler moduli because we had this complexified Kähler moduli. So if you combine these modes, the B's, the C's, and the D's with Kähler moduli, you get precisely 4 times H11 scalars, which naturally fit into H11 hypermultiplets. Yeah? So from this expansion, we get H11 hypermultiplets. And then what else can we get? Well, we had the axial dilaton in 10 dimensions, so that just gives you coupling in 2 fields in 4 dimensions. And I can also take these antisymmetric tensor fields and take both of them indices in the 4-dimensional spacetime. That gives tensors in the 4-dimensional spacetime. But 2-index tensors in 4 dimensions are dual to scalars in 4 dimensions, pseudoscalars in 4 dimensions, the Hodge duals. So that gives me another 2 scalars. So this naturally gives me another set of 4 scalars, and that gives one final hypermultiplet. So in total, therefore, you get H11 plus 1 hypermultiplets. Okay. If you think there are other forms, expansion that you can do, you see that they're all related to the ones that I've discussed here. All right, so now we like to go on and break this to n equals 1 supersymmetry in 4 dimensions. And there are basically 2 ways to go on and do that. One is to turn on fluxes, and that leads to the whole story of flux superpotentials and so on. Okay, that's another long story. Unfortunately, I don't have time for it. The other thing you can do is study defects. You can add Dbranes and O-planes to your compactification. That breaks if you If you choose them nicely, that breaks precisely 1/2 of the supersymmetry. So that will also break n equals 2 to n equals 1. So I'm mostly going to focus on, I'm really going to focus just on the defects for a little while, because basically, as I said, I want to lead up to F theory. Okay, so perturbative 2B has two basic Z2 symmetries. It has a worldsheet parity, which just interchanges the left and the right movers. So the way that it acts on the bosonic fields is it interchanges the signs of the axion, the 4 form, and one of the 2 forms. So you can check that that's a symmetry of the Lagrangian if you look at the Lagrangian for the type 2B theory. And then there's -1 to the F left, which is a symmetry with x as -1 in the field if it corresponds to, if it comes from a string mode whose left movers are in the Ramond sector. And so these are all the Ramond fields, have the left movers in the Ramond sector, so they all get mapped to minus themselves. Of course, these symmetries also act on the fermions, so this symmetry will interchange the 2 gravitinos, and this one acts as -1 on one of the gravitinos, but not on the other one. Okay. So you want to consider orbifolds by these kind of symmetries, and in fact we want to consider orbifolds also that involve a further involution, sigma of x6. So the composition of 2 or 3 or whatever number of involutions is still an involution. I'm going to compose a few involutions to get some interesting composite involution, and I'm going to use that involution to orbifold. And now, by definition, orientifold is an orbifold that involves a parity involution, and possibly some of these other involutions, but it has to involve a parity involution. Okay. Now, sigma will typically have some fixed locus on x6, some locus that's mapped to itself under this involution. So this fixed locus is what we call an O-plane, orientifold plane. And they're basic in these kind of compactifications, there are 2 basic orientifolds that we consider. If we want to preserve n equals 1 supersymmetry, there's -1 to the F left times parity times sigma, where sigma is required to be holomorphic and maps omega 3 0 to minus omega 3 0. So this preserves precisely one linear combination of these 2 spinors, epsilon 1 and epsilon 2. I think it's epsilon 1 minus I epsilon 2, if I remember correctly. And the type of object that this leads to is O3 or O7 planes. Why do I get O7 planes, for example? Well, O7 planes would be the fixed locus. So I have 3 coordinates in the Calabiyau, Z1, Z2, Z3. Okay, now let's take something that looks locally like Z3 goes to minus Z3. Okay, and the fixed locus is Z3 equals 0, so that gives me a O7 plane. And if you remember that omega 3 0 locally looks like dz1 wedge dz2 wedge dz3, right? If z3 goes to minus z3, that means that omega goes to minus omega. Okay, so this is a quick way to see the relation between O3, O7 planes and this kind of involution. Okay, the other option which you could do is you could not involve -1 to the F left. In that case, you still want sigma holomorphic and map omega 3 to itself. This situation is compatible with O5 or O9 planes, but I don't really want to do this one. I want to concentrate on this one, which gives you the O7 planes. Now, okay, so you might be thinking at this point, how do we go about finding a Calabiyau of involution? We've hardly discussed, I mean, the only Calabiyaus we discussed so far are things like the quintic and the Qian-Yao manifold. And how on earth do you find involution on those things? Well, there's actually a simpler way to do it. You could just construct a manifold which has involution by construction, and which is Calabiyau. Let's be explicit about it and just do that here. So we want to construct an x6, so that x6 mod z2 gives you b3, okay? And what we're going to do now is we're going to go the other way around. We start with b3, and now we're going to construct a double cover of it, which will be x6. And the double cover will have an automatic involution, and it will be Calabiyau. Okay, so that's this picture here. So I'm going to start with b3, okay? And then what I'm going to do is I'm just going to consider an equation of the form psi squared equals b2. Psi is basically this direction. Okay, so it's a quadratic equation. and B2 is going to be some polynomial on B3. And this has two solutions, so I get two sheets covering B3, so that's what I call a double cover. Okay, and this has a natural involution, just take psi to minus psi. All right. And now the only problem is to choose the degree of this polynomial correctly, such that the double cover is a Calabiyau. Okay, and I claim that this works precisely when, if you take B3 and we define K to be the canonical bundle of B3, so canonical bundle is by definition the top exterior power of the cotangent bundle. It's a line bundle, which we already encountered many times. Okay, so basically you want B2 to be a section of K B3 to the minus 2. Okay. So for example, if you would take B3 equals CP3, a complex projective space of dimension 3, okay, K of B3 turns out to be O minus 4, and so sections of K to B3 minus 2, they just turn out to be polynomials of degree 8 on CP3. Can't be any simpler than that. Just write a polynomial of degree 8 on CP3. Use this equation. Okay, so now I get a double cover of CP3, and I claim that's a Calabiyau. That's another construction of Calabiyaus. But this one naturally has an involution. Moreover, it has fixed points. So if B2 is a polynomial on B3, okay, well, it's going to have some vanishing locus. So what happens at the vanishing locus? Okay, you can try to draw it over here. It's a fixed point of the involution, right? Where psi gets mapped to psi goes to minus psi. Well, psi is 0 there, so it gets mapped to itself. So on B2 equals 0, that's the fixed locus, so that's the orientable plane. Okay. Okay, the other object we need is Dbranes. So, by definition, a Dbranes is a defect in which fundamental strings can end. That's the Dbrane. The low energy world volume theory on a Dbrane is turns out to be a dimensional reduction of the 10-dimensional Superyer-Mills theory. So you just take the 10-dimensional Superyer-Mills theory and do a dimensional reduction from, I don't know, if it's a D7 brane, you do a dimensional reduction from 10 down to 8 dimensions. If it's a D6 brane, you do a dimensional reduction from 10 down to 7 dimensions, and so on. Okay? So that's a very simple way to think about the world volume theory. Now, the other thing, of course, famous fact about Dbranes is that when you have a stack of m-parallel Dbranes, I've drawn only 2 of them here, and then you let them approach each other. So there's a U1 gate symmetry associated with each brane, but now if you let them approach each other and then they coincide, the gate symmetry actually enhances from U1 to the n to U to the n, to UN, excuse me. And the reason for that is that apart from these strings which go from a brane to itself, we have another open string sector which goes from one brane to another brane. And you can quantize that, and that gives you the W bosons of this broken UN gauge group. And the mass of these W bosons is proportional to the length of the string, so the distance between these two branes. So now when the branes approach each other and get on top of each other, these W bosons go to 0 and you get this enhanced gate symmetry. Okay? Now, if you want to preserve the same supersymmetry that's preserved by the ones which gave you O7 planes, so the -1 to the F left P sigma, then that's also the same supersymmetry which would preserve D7 branes and D3 branes, at least if you wrap them on holomorphic submanifolds of X6. And for D3 branes, you have to localize them at points on X6. Yeah, I'm stating that. I didn't derive it here, but they can derive that. Okay. This slide. Okay, so I do this. Yeah, I tried to squeeze this in, but I don't really need it for anything else, but just for general educational purposes. Let's say a little bit more about this world volume theory and try to make a connection with some of the things that we saw for heterotic strings. Okay, but I'm not going to use this for anything either today or tomorrow, so if you wish, don't have to understand it. So let's suppose we have a stack of these 7 branes with some UN gauge symmetry, and now let's wrap it on a holomorphic submanifold S of X. Particularly for D7 branes, I want to wrap them on a 4-cycle, that is a complex surface inside the Calabiyau. And let's look at the equations for these world volume fields. So the bosonic fields, again, it's the dimensional reduction of 10-dimensional Mills, so it's 8-dimensional Mills, which has an 8-dimensional gauge field, And for the dimensional reduction, 2 of the components of the gauge field get converted to 2 scalars, right? Adjoint scalars. And usually we combine them in a single complex scalar. And the complex scalar, if you remember the way that this works, this complex scalar describes deformations of the Dbrane in the direction normal to it. So if you move around the expectation value phi, you're eventually moving around the Dbrane, the D7 brane in this case, in the higher dimensional spacetime. Okay. It probably should come as no surprise that since the world volume theory is dimensional reduction of 10-dimensional Young-Mills, which is what we saw for the heterotic string, it probably should come as no surprise that the equations, if you want to preserve supersymmetry, the equations that the gauge field A and the adjoint field phi has to satisfy are just the dimensional reduction of the Hermitian Young-Mills equations that we saw for the heterotic string. Okay. So we can do that. So how do we do dimensional reduction? Well, we take our Hermitian Young-Mills connection. So it had 3 components, right? dz1 bar, dz2 bar, dz3 bar, and it depended on 3 coordinates, z1, z2, and z3. And the way we do dimensional reduction is, first of all, we make things independent of z3. So things depend just on z1 and z2. And we replace the dc3 bar component of the gauge field, we replace that by the complex adjoint field. Okay? And now you just substitute that into the Hermitian Young-Mills equations, and you get some set of equations, which, after some manipulation, I'll say a little more about it, essentially is this set of equations. Okay? So that's dimensional reduction of Hermitian Young-Mills equations. And those are the equations that should be satisfied if you want to preserve n=1 supersymmetry. Okay, so a few words to say about this. So first of all, phi, in general, phi should be thought of, and as I said, it describes displacements of the Dbranes in the normal direction to the Dbrane. So usually it takes values in the normal bundle to the submanifolds in which it is wrapped. And you can now use in this case, you can use the holomorphic free zero form to map a section of the normal bundle to a 2,0 form on S. Okay? So you can think of phi here, in this case that we're discussing, the 7 branes wrapped in holomorphic 4 cycles, you can think of them as 2,0 forms on S. Now there's something funny going on here in that 2,0 forms on S transform under the Lorentz group of the world volume theory of the 7 brane. Right. So phi normally doesn't transform under Lorentz transformations along the 7 brane world volume. It does transform under a U on R symmetry, which is R charge 1 or 1/2, I forgot. But what's happened here is that when it's wrapped on a submanifold of a Calabiyau, you can identify with the 2,0 form, which does transform under a certain U1 part of the Lorentz group along the 7 brane. So this is the general phenomenon of topological twisting. The fact that the R symmetry, this is the U on R in which the phi is charged, gets identified with some subgroup of the Lorentz group of the world volume gauge theory. So this is so in particular. So what you find here is that this Young-Mills theory on the D7 brane is actually a topologically twisted Young-Mills theory. Okay. This is actually a fairly general story. So I did it here for D7 branes. But this happens fairly generally. You wrap some branes on some manifolds, you always find it's the top in some special holonomy manifold. You find this very typical situation that the world volume theory is topologically twisted. Okay, now once these things are 2,0 forms, I can write these equations that I've written here. So the dimensionally reduced Hermitian Young-Mills equations, so there's now a set of equations on S, on the thing on which this 7 brane is wrapped. So it says that F02 is 0. Phi has to be holomorphic, and then there's this condition. This comes from the reduction of the Kähler trace. Remember, we Gij bar, Fij bar in heterotic strings. If you reduce that, you get this equation. This is basically Gij bar, Fij bar, and you get a commutative phi term. And the whole story is basically now similar to what we saw for the heterotic string. So for the heterotic string, we saw that Hermitian Young-Mills corresponds to a polystable holomorphic bundle, and it's the same story here essentially. So the first 2 equations here now give you a Higden bundle, which means it's a holomorphic bundle with a holomorphic section of the adjoint bundle, well, twisted by 2,0 forms. So that's like the analog of the holomorphic bundle in the heterotic string. And this equation, well, good luck trying to solve it. But it's equivalent to saying that the Higgs bundle is polystable, where the slope of a Higgs bundle is just the slope of the bundle. Even the proof of this fact uses Donaldson-Uhlenbeck-Yau. Yes, it's completely analogous. Okay, so these equations, again, you'll see them fairly often if you do this kind of dimensional reduction. So it should remind you of Hitchin's equations. So Hitchin studied dimensional reduction of the anti-self-duality equations, 4 down to 2 dimensions, and you got equations which look very much like this. So this is a general story, actually, that you find for branes in the Calabiyau or some special holonomy manifold. Okay, as I said, this is for educational purposes. I'm not going to use it all, actually. Okay, I did want to be a bit more concrete about the typical cycle that a D-brane can wrap in Calabiyau geometry when there's also an Oriental present. At some point I'll show you that this comes very nicely out of F-theory, so I just want to briefly go through that. We want to wrap a D7 brane on, and now let's just discuss a generic D7 brane, not necessarily a stack, just most generic situation where I have a D7 brane wrapped as a holomorphic submanifold of X6, and we're also going to assume we have Oriental present already, and so we again we take this construction where we start with B3 and we take a double cover to get X6, which is a natural evolution. It's given by an equation xi squared equals B2, where B2 equals 0 gives you the Oriental plane. Okay, and now I want to add some D-branes to that to get some n equals 1 compactification. Now, there's a story here that I didn't really touch on, but when you do these kind of, when you start adding branes, you have to be careful that that certain tadpole cancellation conditions are satisfied. So these branes, the O planes and also the D branes, they generate their sources for the Ramon flux, and there's an appropriate version of Gauss's law that you have to satisfy, otherwise you have an inconsistent compactification. You can't actually solve the equations of motion. So there's a kind of charge cancellation condition. Now, of course, a D7 brane, famous facts about D-branes is that they're the elementary Ramon charges, Ramon sources. So a D7 brane is Ramon charge plus 1. O7 plane, O7 minus plane is what I want here, has Ramon charge minus 4. O7 plus, I didn't really say what O7 minus O7 plus is, but okay. The O7 plus is positive charge, so it wouldn't help you much. I set minus 4 here. Maybe some of you have seen that it has charge minus 8. Sometimes you see that it's being said that it has charge minus 8. The difference is whether you're thinking about working on B3 or working on X6. If you work on X6, you should think of it as having charge minus 8. If you work downstairs on B3, you should think of it as having charge minus 4. Okay, so you need a certain number of D7 branes to cancel the Ramon charge of this O7 plane. Otherwise, it doesn't work. You can't satisfy Gauss's law for some of the Ramon fields. And the way that works out is that, so the O7 plane is wrapped in B2 equals 0. Then I need the D7 brane to be wrapped on a manifold of type B8 equals 0, or B8 is a section of K B3 to the minus 8. So it was minus 2 for B2, and it's minus 8 for B8. Very briefly, why is that? Well, so what sources are we talking about here? We're talking about the source for the Ramon axion. So it has a field strength which is one index. It's F1. And Gauss's law then basically says that D of F1 has to be 0 through any closed cycle. Okay. Let's take a closed cycle A. So D of F1 for that has to be 0, but it gets sources whenever the D7 plane intersects A and whenever the O7 plane intersects A. Okay, so this is supposed to be intersection number. So let's say that A times D7 is the intersection between A and D7, and A dot O7 is the intersection between A and O7. But this is 1 unit of Ramon charge. This is minus 4 units of Ramon charge. So if you want no sources for F1 for the 2 cycle, if you want to satisfy Gauss's law through the 2 cycle, this has to cancel. These intersection points have to cancel. It's to be 0 net intersection. And that's precisely this condition of B8 is a section of KB to the minus 8. Now there's actually further subtlety, which I'm not going to explain, but you can find explanation in the notes. I just stated. Why that is you have to find in the notes. Turns out that when a D7 and an O7 plane intersect, you can't have a generic intersection. It's not compatible with Oriental folding. Whenever the D7 brane intersects an O7 plane, you have to have a kind of double intersection. There has to be another piece of the D7 coming in and intersecting it at the same time. In other words, you get an equation. So let's set you get this equation basically where you set, let's set B6 equal to 1 temporarily. So you get an equation for type xi squared equals something else squared, which is singular, but it means you can factorize this xi minus something, xi plus something. So you have two D-branes which come in and intersect each other right at the Oriental plane. Okay, so that's necessary. So that's necessary for consistency. And so the upshot is I can't have a generic section B8 equals 0. I need to have something of the form B2 B6 minus B4 squared equals 0. Otherwise, it's not consistent. But this is it now. So what do I need if I want to write down a compactification of type 2b with D-branes and O7 planes? Well, I can use, say, CP3. I construct a double cover to get a Calabiyau. Okay, and then I take three polynomials, B2, B4, and B6. And B2 equals 0 is my Oriental plane. B2, B6 minus B4 squared equals 0 is my D7 plane. Voila. Okay, the only thing you still need to do is to find a gauge field on top of it. But that's the complete generic form of a D7-O7 compactification. Okay, I have a very brief discussion of Oriental actions on the D-brane. So, of course, the world volume fields also, you have to be careful that you project the world volume fields correctly when you do an Oriental projection. Okay, the way it works is as follows. Parity basically takes A to A transpose. And, of course, you have an action of sigma, so you also have to pull back along sigma. And it turns out that on the massless modes, there's a -1. And finally, this only needs to be true up to a gauge transformation, so we actually do this up to a constant gauge transformation, gamma inside UN. And it turns out there are basically two possibilities. Either gamma inverse gamma transpose equals 1 to a gauge transformation. Well, okay, sorry. So we want to have this, and we get a nice involution. And it turns out that you have basically the following possibilities. You have either two stacks of branes which are interchanged. So I start with a UN gauge group here in this stack and a UN gauge group on the other stack. And then by quotienting out, I just get a single UN gauge group on that stack. Okay, so that ends up with a UN gauge group. The other possibility is that, a stack of branes gets mapped to itself. That means it coincides with an Oriental plane. And then you can have either gamma transpose is equal to gamma, perhaps again up to a gauge transformation. You can put this in a standard form by taking gamma equal to the identity, and then you see that this just says that after projection, you're left over with an SON gauge field. And on the other hand, the other possibility is gamma transpose equals minus gamma, which you can set equal to kind of symplectic form. And then if you project this out, you're left over with a USPN gauge symmetry. Okay? So, by this way, you can generate all these classical gauge group UN, SON, and USPN. Now, for the heterotic string, we had something similar. We had a SO32, and when you compactify it, you can also get SON, of course, and UN, and I think even USPN. But there's also this other heterotic theory, E8 times E8 theory, which had exceptional gauge symmetry. But from this construction, from open strings, you don't get exceptional gauge symmetry. Okay, you get the classical groups, you do not get the exceptional groups that we had for the heterotic string. So this will be different when we go to strong coupling, when we go to F theory. You actually do get exceptional gauge groups. But just from ordinary open strings, you only get the classical gauge groups. Okay. Finally, what I need from type 2b is the story of S-duality. So type 2b has an exact strong-weak coupling duality, which takes the string coupling to 1 over the string coupling. Okay, this is one of the famous dualities of string theory. All the string theories have some kind of strong coupling behavior, and the 2b theory is self-dual under taking the coupling to be large. Now, it's usually more convenient to talk about the axial dilaton, which is this complex combination which involves the string coupling as well as the Roman axion. And G string goes to 1 over G string, this corresponds to tau goes to 1 over tau. And further, the axion, of course, it's a pseudoscalar. It has a shift symmetry, so it's the Lagrangian is invariant under if you redefine C0 to C0 plus some constant. It turns out that that's only Dbranes. It's not invariant if you also have Dbranes present. If you have Dbranes present, then it's only invariant under a shift by 1 or a multiple of that. Now, how does that act on tau? Well, it just acts on this part, so it takes tau to tau plus 1. And of course, these two generations, a famous fact that these generations together, they generate an SL to Z duality group, which takes tau to A tau plus B, C tau plus D, where A, B, C, D is integer matrix with determinant 1. Okay? And at some point I think I'll need it, that B2 and C2 turn out to transform as a doublet under this SL2Z. Okay, now, so what happens with a fundamental string when you take it to strong coupling? Well, it's identified with a D string of the dual theory. So S-duality takes a fundamental string to a D string. But that's just under this transformation. Now we could do general SL2Z transformations, right? Because these generate the whole SL2Z group. If you do general SL2Z transformations, you take a fundamental string to what's called a PQ string. So there's an object in type 2B, which is a PQ string, which is a bound state of P fundamental strings and QD strings. Okay? A 1-0 string is just a fundamental string. A 0-1 string is a D string. And everything else is a bound state of fundamental strings and D strings. Okay? And then the final thing I need is, so we said that a D7 brane is a place where fundamental strings can end. Okay, now apply dualities, you get PQ strings. And so, of course, by dualities, we then also get PQ7 branes. So we define a PQ7 brane to be a 7 brane where a PQ string can end. Okay, so that was really a lightning quick review of type 2B. That's more or less all I need for the rest of the day and for tomorrow. Okay, so F-theory is a little different from what we've seen so far. So far we've seen 10-dimensional string theories with weak string coupling, strings around. And somehow what happens in F-theory, so in F-theory somehow what we want to do is we want to go to finite coupling. And it turns out that in some cases you can make sense out of that. And all the structures that we've seen previously, they are somehow translated into geometry. They're somehow geometric structures. And the things we saw in type 2B in the heterotic string, they come out in certain limits of these structures. But this is somehow a bit more geometric theory. Which also happens to describe strings with finite coupling. Okay, so let's first remind ourselves a bit about elliptic curves. So an elliptic curve is just a 2 torus, and a 2 torus has 2 1 cycles. Excuse me, it's a typo. There should be an H lower one. Well, of course, H upper one is also Z2, but I want H lower one. So H lower one is generated by 2 2 cycles. There's an A cycle and there's a B cycle. And the A cycle has self-intersection 0, the B cycle has self-intersection 0, and A and B intersect in, well, the way I drew it, it seems like there's 2 intersection points, but really there's only 1 intersection point over here. Okay? So the 2 torus has a single complex structure parameter, and the way we get it is as follows. We take a holomorphic 1-0 form on the elliptic curve. So it's a Calabiyau, so it has a holomorphic 1-0 form, right? And now I just take the ratio of the B period and the A period. And if you remember that, okay, so holomorphic 1-0 form is not defined, it's only defined up to a scale, but if you take this ratio, then the scale cancels out. Okay? So we're going to use this period to parameterize the complex structure of a 2 torus. And so this is often called a modular parameter. And the reason that it's called a modular parameter is because there are certain identifications you have to make. So there's certain values of tau for which, different values of tau for which you get the exact same elliptic curve. And so you want to identify them. well, what are these? So there are two basic symmetries. So, so remember, so a torus is really R2 divided by a lattice. And there are two basic symmetries of the lattice. The first one has the effect of just, which gives you the same two torus. The first one has just the effect of changing the A cycle and the B cycle, just permuting them. Okay? And if you look at this expression, well, if we permute the A cycle and the B cycle, that just takes tau goes to 1 over tau. And the other thing you can do, which leaves the lattice invariant, has the effect of taking the A cycle to itself and the B cycle to a B cycle plus A cycle. Again, that will give you, so there's a symmetry that gives you the exact same elliptic curve. And the way that acts, if you do this on tau, you find that tau goes to tau plus 1, right? Because it's B goes to B plus A, so this goes to period of B plus period of A over period of A, so that's tau goes to tau plus 1. Okay, now we just saw these dualities. That's why I discussed them in type 2b. In type 2b, we have an axiodilaton, and in axiodilaton, you also have to make these identifications due to S duality and due to the shift symmetry of the axion. Okay, so the axiodilaton of type 2b behaves just like the complex structure parameter of an elliptic curve. So why don't we make use of that? So let's take our type 2b spacetime, and now let's just attach a torus to it at every point on the type 2b spacetime. And then we have to say what we mean by that. So what we mean by that is that the complex structure parameter of that extra torus that we attach to every point in our spacetime, we're just going to identify that with our axiodilaton. That's going to be our tau. Okay? And then, of course, the torus is an area. We're just going to ignore the area of the torus, or take it to be 0 if you wish, or something. Okay? So this construction is called F-theory, and this is 12-dimensional compactification of F-theory because I started with 10 dimensions and added 2 dimensions, and now I'm in 12 dimensions. This type of construction where we think of the axiodilaton as the complex structure parameter of an extra torus, this type of construction is called the F-theory compactification. Okay? So just again, in the picture, here we have the type 2b spacetime. We add this torus, whose complex structure is the axiodilaton. And now we have 10 plus 2, which is 12 dimensions. Okay, now it's not so interesting if you just take a constant torus. What we want to go and do now is we want to go and fiber this elliptic curve over the type 2b spacetime. In other words, we're going to consider backgrounds where the axiodilaton varies over the type 2b spacetime. Okay? So we want to write elliptic fibration. That is a fibration by elliptic curve over the type 2b spacetime. And here's an explicit way to do that. So you can think of, we already saw before that you can think of elliptic curve as a cubic equation in CP3. So here I've written it in a fine form. It's a cubic equation. If I add an additional fine parameter, y squared is x cubed plus fx plus g. So f and g are just coefficients. This is really an equation of y and x. It's two complex variables, one equation that gives you a curve. It's a cubic equation. It's going to give you an elliptic curve, torus. Okay, so that's a nice way to write, explicitly write the equation for an elliptic curve. And now we want to vary this over the type 2b spacetime, which basically means that f and g are functions of coordinates on the type 2b spacetime. More precisely, they're sections of certain line bundles over the type 2b spacetime. Okay. Okay, and why do we do that? Well, the axiodilaton, you see, the axiodilaton is really, if it's varying over the type 2b spacetime, it's a really nasty thing to work with. Because it typically has branch cuts. So it has this tau goes to tau plus 1 identification, it has this tau goes to 1 over tau identification. And as you go around to type 2b spacetime, you typically have to identify things, and so you're going to get branch cuts. The axiodilaton is typically multi-valued over the type 2b spacetime. So it's very nasty to work directly with the axiodilaton, varying axiodilaton over the type 2b spacetime. You have to deal with all these branch cuts. It's very nasty. In this way, it's very easy, because we can specify a polynomial f and specify a polynomial g on the type 2b spacetime, and they're completely globally defined. There's no branch cuts whatsoever. Okay, just a bunch of polynomials, CP3 or whatever. There's no branch cuts. So this is much simpler to work with, and it still contains the same information because by computing the periods, you've implicitly determined the actual dilaton. Okay? But now I don't have to deal with all the multi-value. So this is a very efficient way to deal with the multi-valuedness of the actual dilaton. That's why it's so nice. Another important point that I have to make is that we are really considering varying actual dilaton over the type 2B spacetime now. So it has some non-trivial profile, which means in particular that the string coupling is typically sum of order 1. It's non-zero. So this is not a perturbative type 2B compactification. In perturbative type 2B, the string coupling has to be infinitesimally small. Okay? Here it has some profile, it varies over the space-time, and typically it's somewhere of order 1. So it's a little bit similar. It's not exactly the same, but it's a little bit similar to M theory versus type 2A. Okay? So type 2A is a string coupling, and type 2A is really only valid if the string coupling is infinitesimally small. But you can go to strong coupling, give a finite expectation value for the dilaton, and then you effectively work with an M theory background, 11-dimensional supergravity background, which contains the type 2A spacetime plus an extra circle. Right? And the size of that circle can vary, but it's non-zero, and that describes a finite 2A strings at finite coupling. Now, f and g depend on coordinates on this type 2B spacetime. And generically, you get a nice smooth elliptic curve. Okay? But it's not always like that. So if you tune the coefficients a little bit, then this elliptic curve can become singular. Okay? If you're going to vary it, that's going to happen. It's bound to happen at some point. Why? Well, you can just compute where it goes singular, and it turns out this curve turns out to go singular when this particular combination is 0. The particular combination is 4f cubed plus 27g squared. F and g are these coefficients here. So this combination is often called the discriminant. And when the discriminant vanishes, this elliptic curve has become singular. And the simplest way it can become singular, remember we had an A cycle and a B cycle. The simplest way it can become singular if one of the A cycles contracts to 0 size. It pinches to 0 size. Okay, and now I have a singular point. That's the simplest way it can become singular. Okay? But remember that f and g were functions, or really sections, line bundles over the type 2B space-time. And now we have a single condition when this elliptic curve goes singular. Okay? So that's a single condition, a single complex condition. So this is going to happen over a codimension 1. So where is delta equal to 0? Well, it's a codimension 1 subset in the type 2B space-time. Complex codimension 1 subset in the type 2B space-time. Real codimension 2 subset of the type 2B space-time. So we have this type 2B space-time. We have elliptic curve varying over it. And now there's some complex codimension 1 subsets of the type 2B space-time where this elliptic curve goes singular. Okay, now there's bound to be something interesting there. So let's try and figure out what it is. Okay, so, all right, so here I've tried to draw it. So here we have our type 2B space-time. So here, away from this point over here, away from this special point over here, I just have a smooth elliptic curve. And so for this special point here, the elliptic curve becomes singular, and this is one cycle which is contracted to 0 size. Okay? Now, this situation is actually well studied in monodromy. What happens is that there's monodromy on the cycles. So if I take a smooth elliptic curve and I transport it and then come back to myself, there's a monodromy on the 1 cycles of that elliptic curve. So the elliptic curve comes back to itself, but the 1 cycles aren't quite the same. And they're related by the Picard-Lefschetz formula. So if there's an A cycle shrinking to 0 here, then under this monodromy, what happens is that AB goes to A, B plus A. A here is the cycle that's shrunk to 0 size. Okay? And if you remember how that acted on, the actual dilaton or on the smaller parameter, this corresponds to tau goes to tau plus 1. Yeah? So, well, this is the simplest case where I assume that the A cycle goes to 0. In general, you would get tau goes to A tau plus B or C tau plus D. Which is the simple one, just the A cycle shrinks. Okay. So you see that there's a monodromy. So there's a monodromy of these cycles, but therefore there's also a monodromy of the axiodilaton around this locus where you get the singular fiber. Okay, so this was what I was talking about before. The axiodilaton in these compactifications is multi-valued. There's a branch cut over here. Okay, and if you go across it, all goes to plus 1. But now what does this mean from the type 2b perspective? Okay, well, let's take a little disk here. Let's take a circle and let's fill it in with a disk. And let's take the normal axion and let's take its field strength and try to integrate it over the disk. And well, what I really want to do, I want to integrate the axion around the boundary of this disk. All right. So morally, that's this, but this can be singular in the interior. And but now remember, so now I want to compute the integral of the normal axion around this circle here, which surrounds this discriminant locus. But now remember that tau goes to tau plus 1, or equivalently, so just above and below the branch cut, C jumps by 1. Right? So, I'm sorry?
Shouldn't you have D in the middle?
Oh. Shouldn't have what? Sorry.
Shouldn't you have D in the middle integral? D1. And the integration by parts.
They're doing integration by parts. I'm using Stokes, so I'll go to the boundary of the disk.
Yeah, but how do you get the extremal value?
The difference between them. So this is what I was trying to say. So so my 0 and 2 pi, I'm gonna think of them as just being above and below the branch cut.
C naught is a 0 form, right?
Yeah, it's 0 form.
So to integrate it, you need
I'm sorry. Oh boy. Oh, that's not good. Right. Yeah, I'm sorry. There's a D here. I'm sorry. Right, and the source is, of course, a D of f. Okay, I'm sorry. Right, so D of f is a 2 form, and source is delta 2, which is localized. Okay, so I got this screwed up. I'm sorry. So, right, so the source is actually, a normal flux is sourced by, for D of f1, so there should be an extra D here. Okay, fine, thank you. Yeah, okay. So this should be D. There should be D's everywhere. Add the D's. But the point is that there's, so there's this jump. Okay, there's this jump as you cross the branch cut. And so as you jump the branch cut, so you end up with a value 1 for this integral. Okay. And so what this means that, again, if you add the D, okay, what this means is that there's a source for the normal axion sitting inside this disk. Okay. And of course, I can contract the circle as much as I want. So the source is really associated with this discriminant here. And therefore, well, we've seen before that what's the thing that sources one unit of Ramon flux? It's a D7 brane. Okay. So from the type 2b perspective, this discriminant locus here, there's a D7 brane sitting here. That's what it means. Okay. And that's for the simplest case where you have a 1-0 cycle shrinking to 0 size. So more generally, if you have a PQ circle shrinking to 0 size, you get this particular monodromy, and it corresponds to a PQ7 brane. Okay, it's by isomorphism monodromies. Okay, I have 5 minutes. Okay, let me just get started on this. Okay, so I've tried to motivate this F-Fourier picture from a type 2b perspective. Okay, so we have this axiodilaton. We added an elliptic curve describing the modular parameter, describing this of the elliptic curve, identifying that with the axiodilaton. We have this elliptic vibration over the type 2b spacetime, and we've seen that the singular fibers correspond to 7 branes. These 7 branes are PQ7 branes. Okay. Now I want to discuss this from a slightly different perspective, which is the M-Fourier perspective. And so at least for this slide, I'm going to temporarily completely forget about F-Fourier, and in the next slide we'll see how it's related to F-Fourier. So for just one slide, I have to talk to you about M-Fourier. Okay. So M-Fourier, well, when I mean by M-Fourier, I'm really just going to look at 11-dimensional supergravity. And what I'm going to be interested in, and what's going to be relevant for F theory, is if you consider a compactification of M theory with down to 3 dimensions. So I start with 11 dimensions, and I take a Kaluza-Klein ansatz of the form Minkowski times 8-dimensional real manifold. Okay. And so this is a compactification of M theory down to 3 dimensions. And further, I want to preserve n equals 2 supersymmetry. Right? This time I don't want to preserve n equals 1 supersymmetry, I want to preserve n equals 2 supersymmetry. The reason being that eventually this will be related to n equals 1 supersymmetry in 4 dimensions. But basically n equals 1 supersymmetry in 4 dimensions reduced to n equals 2 supersymmetry in 3 dimensions. Okay. So I want to have n equals 2 supersymmetry. Now, why is some 8-dimensional real manifold? And just as we've already seen for the heterotic string, and just as we've already seen for the type 2 string, there's the usual story. If you want to preserve some supersymmetry, you look at the supersymmetry variations, in this case the 11-dimensional supersymmetry variations, and you're trying to find some unbroken generator. You're trying to find some supersymmetry that's not broken. And again, there are fluxes here, but I'm going to ignore them. I'm going to set the fluxes to 0, and then there's a gravitino. And so the usual equation is that the variation of the gravitino is proportional to covariant derivative of a spinner. There's a 3-dimensional part and an 8-dimensional part. 3-dimensional part is constant. And so preserving a supersymmetry equation, just as all the times we've seen before, it corresponds to finding a covariantly constant spinner on this internal manifold Y. Okay? Spinner here lives in the 8-dimensional chiral, positive chirality spinner representation of SO8. So spinner representation of SO8 are 8-dimensional. Okay? So that story seems much like we've seen before. But the difference here is that I need n equals 2 supersymmetry, not n equals 1 supersymmetry. So in order to get that, and since I started with a single spinner supersymmetry parameter in 11 dimensions, in order to get 2 unbroken supersymmetries, that means I need 2 covariantly constant spinners on Y, not 1. Okay? Okay, so we take this 8-dimensional spinner representation, and normally we would have decomposed it as 1 plus something else. Now I want 2 covariantly constant spinners, so I really want to decompose it as 6 plus 1 plus 1. And these 2 1s are the 2 covariantly constant spinners that I need to get n equals 2 supersymmetry. Okay? But what's the subgroup which fixes 2 spinners in, yes?
5, 1.
Okay, yes. Okay. What's the subgroup that fixes 2 spinners inside SO8? Well, that's spin 6. And spin 6, if you remember, is SU4. Okay. So the holonomy group of this 8-dimensional manifold has to be SU4 if I want to get 2 covariantly constant spinners. Okay. But SU4 inside SO8, that's the usual, again. So you start with a manifold which has SO8 holonomy, which is the generic thing. Okay. Remember, if it's scalar, it would have U4 holonomy. And if it's Calabiyau, it would be SU4 holonomy. Okay. So SU4 holonomy corresponds to a Calabiyau 4-fold. Okay. So we've seen Calabiyau 3-folds quite a bit now. But in this story, if you want to take M-theory compactifications from 3 dimensions down to 3-dimensional n equals 2 supersymmetry, what you end up needing is a Calabiyau 4-fold. So now we're going to talk about Calabiyau 4-folds. Okay, so now we go and try and put F-theory back into the game. So what I want to use to relate F-theory to M-theory is the following. We're going to use a relation between type 2b and M-theory, and it's the following relation in 9 dimensions. So let's consider M-theory compactified on an elliptic curve, M-theory compactified on T2. So the claim is that this is equivalent to type 2b compactified on a circle of radius r. And that the way the identifications work is that the modular parameter, that is really the axial dilaton, well, sorry, right. So the modular parameter of Tt2 corresponds to the axial dilaton on the type 2b side. And area of Tt2 corresponds to the inverse radius of the circle on the type 2b side. Okay? Okay, so now what we're going to do is we're going to take our M-theory compactification to 3 dimensions on Y on a Calabiyau 4-fold. And we're going to assume that in addition it has an elliptic vibration. In addition, it's fibered by elliptic curves. So roughly speaking, it's of the form B3 times T2. It's not a direct product, it's really a fibration, so it's kind of a funny way to write it, but just so you see the factors. So there's a complex three-dimensional manifold here, and then there's an elliptic curve on top of it, which makes a fourfold, a complex fourfold, and this is our Calabiyau fourfold. So we're going to do M theory on three-dimensional Minkowski space times that fourfold. And now we're going to apply this duality fiber-wise. M theory, so M theory on Y, so it's going to be M theory on R12 times B3 times T2, roughly speaking. But M theory on T2 is 2B on S1, so this is equivalent, if you do this fiber-wise, it's 2B times R12 times S1 times B3. And then on top of that, there is somehow this elliptic curve. But this elliptic curve, again, from this duality, it's not really an elliptic curve, it's part of the space-time. It's the elliptic curve which encodes the axial dilaton. Okay? So this comes from applying this duality fiber-wise. Now what we're going to do, so we have Minkowski space times a circle, and now we want to decompactify the circle in order to recover a four-dimensional Minkowski space. Okay? How do we do that? Well, we take the radius of R to infinity. So that means that on the M theory side, where the radius was identified with 1 over the area of the torus, okay, that means that you have to take the area of the torus on this side to 0.
You see that the T2 on the right?
No, so yeah, so as I said, so the T2 here, I should try to cover it here. So the type 2B spacetime is R12 times S1 times B3. And this T2, you don't really have it. According to this duality, you don't really have the T2 here. It's just, you just identify the modular parameter with the axial dilaton of the type 2B. So I only left it in here to emphasize that there's a varying axial dilaton over the type 2B spacetime. This is not really part of the type 2B spacetime. Okay, so if we compactify this circle, and this, by taking the area on the M theory side to 0, and we get this type 2B on R13 times B3 times T2. And now you can also see where, so n equals 1 supersymmetry reduced in the circle in 4 dimensions gives you n equals 2 in supersymmetry in 3 dimensions. That's why I wanted n equals 2 supersymmetry in 3 dimensions. Okay, so from this, taking the circle, opening it up, you also recover n equals 1 supersymmetry in 4 dimensions. So the upshot of it is that if I take an M-theory compactification on an elliptically fibered Calabiyau, and then take the area of that elliptic fiber and shrink it to 0, then there's another circle that opens up, and it's equivalent to a type 2B compactification on R13 times B3 with extra elliptic curve, which varies over your type 2B spacetime, or equivalently, this is an F-theory compactification on R13 times Y4, B3 with the elliptic curve. Where again, elliptic curve is the axial dilaton. And so this gives a compactification of F-theory on a Calabiyau fourfold to 4 dimensions and preserves n equals 1 supersymmetry. So I think this is a good point